we are going to learn Lampel Ziv coding, which is another coding method, source coding method. It is different from Huffman coding in many respects. First of all, one major problem with Huffman coding is that it requires symbol probabilities to be known in advance. But most real-time applications do not provide the symbol probabilities in advance. If you have got a recorded file, audio or video or some text file which you want to encode, in that case Huffman coding is possible, or it is easy to be done because its data is already known. But if you want to apply it on a real-time application, for example for video conferencing or for voice chat, then this kind of source coding is not very practical, because we do not know the probabilities of the symbols in advance. Also, while Huffman coding is optimal for DMS source where the occurrence of one symbol does not alter the probability of the subsequent symbol, it is not the best choice for a source with memory. So there is another limitation of Huffman coding, that is, it is best for memoryless source or memoryless channel, but it is not memoryless channel but memoryless source, but it is not a best choice for source with memory. Example of source with memory is the letters which occur in pairs or group like Q, U, TH, ING, etc. As you can see over here, this in English, if Q has appeared in the text, then most probably the next letter after Q will be U, because I believe there is no word in English which is in English where Q is not associated with, and Q or U are not together. U always comes after Q in English. So if that we know that the dependence of U on its previous letter, that is Q. Similarly, for many words like this, that, and those, TH comes in combination like over here, and ING is also always is in mostly in combination for words which end in ING, for example going, coming, like that. So Lampel Ziv does not need source symbol probabilities. This is the main and basic advantage of Lampel Ziv coding. In Huffman coding, probabilities are required. In Lampel Ziv source coding, symbol probabilities are not required. Lampel Ziv coding belongs to a class of universal source coding algorithms, that is, algorithms that are independent of source statistics. So the algorithms which do not imply probabilities or source statistics are called universal source coding algorithms. It is a variable to fixed length source coding algorithm. This means that any sequence of source outputs is uniquely passed into phrases of varying lengths, and these phrases are encoded using code words of equal length. Method of coding. Parsing, that is reading the bits, is done by identifying phrases, combination of ones and zeros, of the smallest length, minimum number of bits that have not appeared so far. The parser observes the source output, and as long as the new source output sequence after the last phrase coincides with one of the existing phrase, no new phrase is introduced and another letter from the source is considered. As soon as the new output sequence is different from the previous phrases, it is recognized as a new phrase and encoded. The encoding scheme is simple. The new phrase is the concatenation of a previous phrase and a new source output. To encode it, the previous phrase and the new bit are concatenated. So Maybe it is not very much clear in wordings, but when we'll go through an example, that all these steps will become clear. Let's assume we want to parse and encode the following sequence. This is a sequence of incoming output stream, and we have to encode it using Lampel Ziv coding method. What happens is that first of all, this 0 is received. The first receiving bit is this 0. The Lampel Ziv encoder will look into its buffer portion, which it calls dictionary, and will try to find if this 0 is stored over in that buffer area or not. Since this is the first bit or first symbol which is received by the encoder, the buffer is empty. Since the buffer is empty, it will not find this 0 over there, so it will output this 0 as it is, and it will add this 0 in its buffer with at some specific location, giving it an index number or location number. After that, it will receive 1. Again, this 1 is not in the dictionary, so it will output this one as it is, and it will also store it another index number. Suppose the index number given to 0 is 1, then the index number at buffer given to 1 is 2. Then it will combine these two zeros. Why? Because when this first 0 will be received by the encoder, it will again look into its dictionary, and it will find that this 0 is already in its dictionary at index number 1. So what it will do, it will just combine this 0 with a new 0 which is received over here. Then it will receive this 0 and this 0. It will know that this 0 0 is already in its dictionary at location number 3. So it will combine this 0 0 with this new bit 1 over here, and it will add a new phrase in its dictionary, that is 0 0 1. Then when it will receive this one over here, then it will see that there is 0 after that. So this combination does not exist in its dictionary, but 1 exists in its dictionary. So first of all, it will look for 1. It will find it at location number or index number 2, and it will concatenate it with this new bit which is 0, which is over here. So this new phrase is formed, which will be saved in its dictionary again, and it will be output as well. So after that, this new combination is formed. Here these two zeros are already there in the dictionary at location number 3, and these two zeros are combined with this 0 to form a new phrase or new group which is stored at location number 1 2 3 4 5. So this way it will go keep going on. It will receive this 1 0. Of course, this 1 0 is already in the dictionary, so it will combine with this new one, and a new phrase is formed, that is 1 0 1, and this new phrase is added into the dictionary again. Then it will find these 3 zeros are already there in the dictionary. It will combine these 3 zeros with this new 1 0, and 0 0 0 0 combination is formed and stored in the buffer or dictionary. Then this 0 1 is formed. Again, this phrase is stored in the dictionary. This 0 1 0, this 0 1 is already there in the dictionary over here, this one, and this is combined with this new bit 0 over here. So this 0 1 0 is formed. These 4 zeros are already there in the dictionary. These 4 zeros are combined with this one, and a new combination or new phrase is formed, which is 0 0 0 0 1, and it is added in the dictionary again. This 1 0 0 1 0 is already there, so 1 0 is combined with this 0 to form a new phrase which is 100 and added into the dictionary. 000 is already there, it is combined with this 1 over here, and this 00001 is 0001 phrase is added in the dictionary. 010 is there, so 010 is combined with new bit, and 0100 phrase is added into the dictionary. Then 0010 00001 in here. So 001 is already in the dictionary, so it is combined with new bit 0 and a new phrase 0010 is formed and added into the dictionary. And last, this 0100, it is already there in the dictionary, it is combined with this new bit 1 and a new phrase 01001 is formed. After parsing, that is grouping of bits, total number of phrases are 16. As you can count these total number of phrases: 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 and 16. It means we need log base 216 is equal to 4 bits for each phrase plus an extra bit to represent the new source bit. For encoding, we consider all the bits except the last bit. Select the 4-bit code according to the prefix phrase. Now we will go through an further example to understand all these steps. Look over here. First of all, this 0 is received, and after receiving this 0, it is added into the dictionary, and the output is 000, that is the index number of empty buffer, because when there is no initially the buffer is empty, there is no bit is stored in it, so initially the index number is 00, that is empty, so this index number is added with this new bit which is 00000. This 0 is the phrase which is output, at the same time it is added into the dictionary, and this 000 is the location index of the previous phrase. Since there was no previous phrase, so the index number is 4 zeros. Now this 1 is received after 0. Again, this 1 is not in the dictionary anywhere, although this 0 is added at location or index number 1, but this 1 does not exist in the dictionary, so the index number for this 1 is, again, there is no concatenation. No concatenation means index number is 0000, so these 4 zeros are concatenated with this new bit 1, so this is a new code word. Then 00 is received. Now in this 00, this 0 has already been received by the encoder, and its location, it is stored in the dictionary at location 0001. So first of all, instead of transmitting this 0, we simply transmit its location or index number. So its index number is 0001, which is concatenated with this new bit, so the new code word for this one is 00010. The next combination is 001. This 001, for this 001, this 00 is already there in the dictionary at location number 0011. Again, instead of transmitting 00, we just simply transmit its location or index number, which is 011. So 0011 is concatenated with this new bit 1, and the total code word is 0001. 111. Now 10 is received, then this 1 is already there in the dictionary at location number 0010 in the index, and instead of transmitting 1, we just simply write its index number, which is 0010, and it is concatenated with this new bit 0 over here, so the code word is 00100. By the way, as you can see, this is simply this corresponds to decimal 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. So after this one, this 000 is received. This 00 is already there in the dictionary at location number 0011. Again, the location of this 00 is transmitted, so 011 is concatenated with 0. After this 101 is received. 10 is already there in the dictionary at location index number 0101. So 01 is concatenated this new bit 1, and that code word 01011 is transmitted, and it will keep going on like this until this one. In this case, no compression is achieved. In fact, before compression, the total number of bits was 49, but after applying LZ77 compression, the number of bits have increased to 80. As you can see, if you'll count the total number of bits over here from here to here, they are 49. These are 49, 02, 01, 001. But if you, when after decoding, the total number of bits have increased. In fact, they have not decreased as we expected it to decrease. They have increased, and they have become 80 from 49. So this compression method is useful for large initial strings. The larger the initial string, the more compression is achieved. So what we understand from this example, although it is a compression method, but it is not an efficient compression method for small input strings or small initial strings. If the initial string is big, then the compression is achieved. Ziv proved that for long documents, the compression of the file approaches optimum efficiency. If you have large files to compress, then what is proven by Ziv, who was one of the two researchers, Lampel and Ziv. This guy Ziv proved that using this Lampel Ziv compression method or source coding method, you can approach optimum efficiency. Although here it looks not performing the job, it has not really compressed the data, but for large files, big long documents, this is really very efficient. The LZ algorithm is widely used in practice to compress computer files. Compress and uncompress utilities under Unix and zip under Unix, and zip, zoo, LZH and ARG under MS-DOS use variants of LZ algorithms. So these, as we can understand from this one, that compress and uncompress utilities are again lossless compression methods, and this one is very efficient method of compressing large files. But it has got an advantage. What is the advantage? That it does not require to know the probability of the symbols. LZ77 encoding example with letters. There is another example. In the previous example, we tried to understand the LZ compression method using bits. Now we will try to understand the same method using letters. There is no difference in the two, but it is just a matter of describing the things and understanding in different ways. So maybe for for those who have not, this compression method is not very clear and they have not understood it very well in the bits form, maybe this example will be helpful. It is called LZ77 because this algorithm was proposed by Lampel and Ziv in a paper in 1977. These are two guys who researched who developed this encoding method, and it is called LZ77 just because it was published in 1977 in a paper. The decoder reads or parses the letters as they are received. The decoder uses some memory space called buffer to store the new letter or group of letters and call it dictionary. When the first letter arrives, at that time the buffer or dictionary is empty and contains no letters in it. The parser reads the first letter, searches the dictionary for that letter in it and finds no match. So it adds this first letter in the dictionary and assigns it an index or sequence number, that is 1 for the first letter. At the time it outputs that first letter with index number and length of the letter found in the dictionary, but for the first letter it is always 0 because the dictionary is empty. So the form of output is like this: index number of the letter or combination of letters found in dictionary, comma, length of the letter or combinations of letters found in dictionary, and new letter. This is exactly the same method or same steps which we have seen in the previous example. That's what we actually did in the previous example. It is explained again in the just replacing bits with letters. For example, input letters are A, B, B, C. Then output for A is 0, 0, A. For B is 0, 0, B, and for C and for BC 2, 1, C. As it is clear from here, for example, when the first letter is received, what it says that this is the location of the phrase which is already stored in the dictionary. Since initially the dictionary is empty, there is no phrase or no no group is stored or no letter or is stored in the dictionary. So this number will always be 0 for the first letter which is received. And since there is no symbol or letter or phrase is added into the dictionary, its length is 0 as well. So this is the location and this is the length of the phrase stored in the dictionary, which is to be concatenated with A. Since we are not concatenating any letter with A, as it is the very first letter and there is no letter in the dictionary before, so this will always be 0, 0. Now for B, it is again 0, 0 because this B is also a new letter, although there is a letter in A, but that letter is not the it has got no combination with this B over here. So this B by itself is a new letter for the decoder encoder, so it simply assigns it 0, 0 again and then writes B. And for BC it is 2, 1, C. After reading B and output it as 0, 0, B, B is added in the dictionary. This is the main important point. Whenever a new letter comes in, of course it is output as 0, 0, A, but at the same time it is added into the dictionary as well at index number 1. And this B is also added into the dictionary at location number 2. So this B is added in the dictionary at index number 2, A is already added at index number 1. After reading first B, when reader again reads B, it searches for B in the dictionary and finds B at index number 2. Then it reads next letter and finds it as a new letter, so it outputs BC with the index number and length of BC with C in form of 2, 1, C. So what it simply does is that it searches for this B, it finds it in the dictionary. As we have seen in this previous example, that whenever we find the phrase already in the dictionary, we don't transmit this phrase by itself, but we simply transmit its location. So here the location was written in binary form. Now here we are writing the same thing in decimal form, just to make it just to understand it. So what it does, that it writes its location number, its index number of b. The previous b is 2, as it is written over here. So this 2 is written over here. What is the length of this b? Is just if you are considering just as a letter, then its length is 1. So its total its output as 2 comma 1 comma c. So this 2 comma 1 simply replaces this b by defining its location and its length in the dictionary, which is already existing, and then at the same time this bc is added into the dictionary as well. Example of LZ77. We will go through this example in the next lecture.